connection from Roberta Sparvoli, whom some of you might know her. She's director of INFN, she's full professor in physics in Tor Vergata, director of INFN Rome Tor Vergata, and she's working many experiments, also many with us, with me, first with the Nina Mita on the Russian satellite in 98, on the Mir space station. Then there is the big Pamela experiment, again with the Russians. Most recently, the two satellites, XS-01 and XS-02, which were done in conjunction with our Chinese colleagues. Now, she's also involved in GAPS, which is another telescope to study antiprotons from the South Pole, and of course in GEMUSO. So I hope she's awake because of the time difference, and also, as you know, today is holiday in Italy, is Immacolata Concezione, so she was doubly kind to join us and give her talk on a general introductory talk. All these have a strong emphasis on physics, so it's a general introductory talk on cosmic rays, history and perspectives for the future of cosmic rays. Roberta, grazie. Parla di...
I'm here. Can you hear me?
Okay. Can you share the slides?
Yes, I switch off the video because I think it was enough for you already to see me. A voi. So thank you very much for inviting me. I'm also calculating the timing. So as Marco said, I will make an introduction on the physics of cosmic rays. Also, some of the things have already been said in this first session. So I will try to summarize our activity in the field and a little bit of history in the field. Second, because I cannot go ahead. Can you see the slides moving? Hello?
Bye. Okay.
Okay. So astroparticle physics is one of the best examples of what astroparticle means, which means unifying the macrocosmos, so information about the universe, and the microcosmos, which means doing this with the tools of elementary particle physics. So how do we study the universe? So we study the universe in astroparticles by looking at cosmic messengers, which are mainly photons and electromagnetic waves. This is what we call astronomy. Cosmic rays, which is what we call then astroparticle physics, so the topic of my talk. Neutrinos, which is a particular field in astroparticle physics, and gravitational waves, which is the most recent and most famous now, but I will not talk about this. So if we study all these components simultaneously, then we really get a clear knowledge of the universe. So cosmic rays are just subatomic particles which come from outer space and hit constantly the atmosphere at a very high rate, considering them a number of particles on the unit of area. As we will see very soon, they cover a huge interval in energy, reflecting the fact that they come from very different origins. They can indeed come from the sun, and these are, let's say, they cover the lower energy part of the spectrum. They can come from the Milky Way, and this is the biggest percentage of cosmic rays, mainly from explosion of supernova, and they come from the extragalactic space with sources like active galactic nuclei, radio galaxies, and blazars, and so on. The composition of these particles is mainly composed by protons, 85% of the component, also nuclei, electrons, and a very small percentage of antiparticle if we talk about the charged component. If we talk about the neutral component, which means without electric charge, we have gamma rays, neutrinos, neutrons, and as I said, gravitational waves, which are not really particles. The neutral component of cosmic rays points directly to the source because they are not deflected by magnetic fields, whereas the charged component, of course, has a very erratic path from the source to the Earth where we collect them. As we will see later, the energy spectrum of this particle resembles a power law. We will see if this is really the case, but as a function of energy, the intensity of cosmic rays follows a quite regular power law with an index which is roughly 2.7 for the galactic part of the spectrum. I will return to this anyway later. We are interested then, when we catch cosmic rays, we are interested to understand its nature. So if it's a proton and a nucleus or a neutral particle, the energy, the direction, and then to understand the source. If we get all this information, we really do astroparticle physics, and we discover the fundamental issues regarding them. The atmosphere acts as a real detector. So if we catch the cosmic rays above the atmosphere, we make direct measurements, which is really the topic of my talk. If we collect them after the interaction in the atmosphere, we make indirect measurements. This will be the topic of a future talk in this afternoon in Japan. So coming from direct measurements, I will talk about measurements on balloons, satellites, and orbiting space stations, because these are the platforms where we conduct these particular studies. So what are the fundamental issues of physics that we want to pursue? I will concentrate, of course, on the most important ones. So the main topics is the solving the problem of the matter-antimatter asymmetry existing currently in the universe and the signatures of dark matter. These are, of course, the hottest topics in particle physics and astroparticle physics, also cosmology, of course. And we are also, of course, interested in the elemental abundances of cosmic rays in general and the way they propagate from the source towards us. So the antimatter issue, what is this about? What is antimatter? I mean, I don't know exactly the audience who's attending this day, but I guess it's a mixture audience. So I will just recall a little bit what antimatter is. Is the symmetric counterpart of the particle in ordinary matter. So these are particles with the same mass and momentum, let's say, and characteristics of matter, but with the opposite electric charge and all other so-called quantum numbers. Particles and antiparticles annihilate each other once they meet, producing products like electromagnetic waves. The most known antimatter that we know that we have produced on Earth is the antiparticle of electron, which is the positron, the antiparticle of the proton, which is the antiproton, and also we produce artificially some anti-nuclei. But the reality is that in the universe, antimatter is negligible, which is in odd with what we expect from the Big Bang model. So our model of cosmology and of particle physics tell us that at the beginning everything was in equilibrium. So the same amount of matter and antimatter should have been produced at the very early stages of the universe. Matter at that time was in the form of so-called baryons, which are like the protons, the neutrons. So we expect a very symmetric universe in terms of baryons and antibaryons, so matter and antimatter. In reality, this equilibrium is not at all what we observe in the universe, where antimatter is really orders of magnitude less than what we expect, and in reality is not of primary origin, what we witness in cosmic rays, for instance. How do we observe it? So we really search in cosmic rays for antinuclei or antiprotons or positrons directly. This is what I will mostly talk about, because I'm not talking about gamma rays, who are also capable of searching for antimatter. Antimatter is indeed present in cosmic rays, but just a secondary production of interaction of normal matter in the interstellar medium. So we see antimatter, but this is not enough with respect to what we expect. The other very strong issue, physics issue, is the search of dark matter. Dark matter is, as mass exists, this comes from very independent observations in the universe, like, for instance, rotation curves of galaxies or gravitational lensing. Dark matter is seen by its gravitational effects on the visible matter. So we don't really see it, but we feel that it exists due to its gravitational effects. Like, for instance, if we measure the rotation curves of galaxies, we measure, you see the yellow light, we observe much stars in the spiral galaxies which move much faster than what is expected if the mass is only in the visible light. So there must be mass hidden, which make stars in the spirals moving faster than what is expected. Other observation, as I said, comes from the gravitational lensing, which is the deviation of light from distant objects towards us in the line of sight due to the fact that there is some hidden mass which really acts as a lens in the direction of light. These are not only, these are the most striking, but not the only effects of dark matter. Finally, the model of cosmology goes under the best accepted model of cosmology goes under the name of lambda CDM model. I will not go into details about this model, but you can see from this apple pie graph that this model predicts a quantity of dark energy, which is very big. This is even a less known quantity in cosmology, and a very high percentage of so-called dark matter. What does it mean, dark? Means that it doesn't have the nature of the normal matter that we know. It's not antimatter, which would still be baryonic, but it's really dark and not known in its characteristics. For instance, dark matter could take the form of a so-called neutralino. This is a complicated particle coming from a theory which is called supersymmetry. Again, this is a theory which would solve a lot of problems in particle physics and would give as natural a good candidate for dark matter. So we are searching in cosmic rays for this neutralino, which should have also resisted from the Big Bang times. And what does this neutralino do? This neutralino is hidden in the hull of the galaxy, again annihilates with its own antiparticle, producing a lot of secondaries which are ordinary matter like gammas, neutrinos, again antiprotons, positrons, and so on. So we are searching in cosmic rays for a possible annihilation of this dark matter candidate. Last but not least, we need to measure the spectra and characteristics of normal matter in cosmic rays, so in the ordinary cosmic rays, because we still don't need exactly what are the sources, and we are not certain about their propagation mechanism. Supernova explosions are most probably the sources of cosmic rays, but we are still debating about their real role. And anyway, if we want to search for dark matter or antimatter in cosmic rays, we must know exactly the signature of normal cosmic rays. So it's really a critical point to go for normal, let's say, ordinary cosmic rays measurements. So coming to the missions, as I said, the three platforms increase in costs and dimensions from stratospheric balloons to satellites up to missions on the space stations. Stratospheric balloons have a lot of pros, which are the budget is limited, the assembly is fast, very often it's possible to recover the payloads. There are, of course, some cons, which are the limited lifetime and the existence of still atmosphere, which in a certain sense needs to be really worked out to measure the incoming spectra. Here are some historical landings of some of our missions. Balloons became very popular once the Antarctic flights were established, thanks to NASA long duration balloon facilities. So in this case, it's possible to have launches which last 30 days or more. And we have very famous mesh missions, Climatic, BESS, Trace, and Tiger missions, and also the missions which were mentioned before by SPB balloon, GMUs or balloons. Satellite flights, what are the cons? Of course, much longer flights and much better statistics, no atmosphere, but much more risky, much more expensive, and not repeatable. Regarding satellites, the most famous missions are the Pamela mission. Marco has already mentioned it. This was a 10 years mission on Russian satellites dedicated specifically to cosmic rays in space. This is not taking data anymore, whereas we have the Dept mission still taking data. This is again a Italian-Chinese collaboration on a space satellite standalone, also dedicated to cosmic rays up to the very high energies. We have the Fermi satellite still taking data. This is mostly dedicated to gammas, but it's made a very important measurements of electrons and positrons still in orbit. NASA, Italy, and other nation missions. And as Marco said the two Italian-Chinese Success and 01 and 02 missions, both still in orbit, dedicated instead to the low energy part of the cosmic ray spectrum, and they are in data taking. Regarding space stations, we have more or less the same pros of the satellite. Of course, the cons are even more severe than the satellites because the missions are even more expensive. There are few launchers, as we know, which can accommodate an instrument on the space stations, few lockings. And of course, there's also requests of safety for humans on board. These are manned environment missions. Of these missions, we have 3 very important missions of cosmic rays currently on the International Space Station. We have the AMS spectrometer, since long now taking data which is giving the most precise charged cosmic ray measurements ever in space. We have the CALET mission. This will be the topic of next talk, so I will not spend too much time describing this very famous and successful mission from the JAXA, Italy and JAXA, of course. And we had for a few years also the CREAM, so the extension of a balloon CREAM mission on the space station. This has taken data only a few years, but nevertheless has given important results. So I will be very fast on a few results of these missions. So regarding antiprotons, there have been Pamela, BESS, AMS measuring antiprotons with not particular expectations. As you can see here on the left panel data compared to theoretical expectations. You see that the data sit quite well on expectations apart from the very high energy side where we have few data. Here I zoom on the energy part. The data are a little bit above the expectations, giving still room for a possible new source. We expect from AMS high energy data to solve definitely this question. Regarding antinuclei, so far no antinucleus, antideuteron or antihelium have ever been measured in cosmic rays. The different has been the story of electrons and positrons, especially the positrons. In fact, measurements by AMS, Pamela, and Fermi, as you can see from this plot, measured a positron fraction much higher. This is the data which compared to the gray band, which are the expectations. You see a very sharp increase in the positron fraction, the fraction between positrons and electrons. If we separate the contribution of positron and electrons, we clearly see that the positrons have a clear bump at high energies, witnessing the existence of a positron source. So this was big expectations for a dark matter candidate, for a new source. In reality, this bump in positrons can be explained also in terms of ordinary astrophysical objects like the pulsars. These are rotating neutron stars which can emit positrons. So far, let's say this bump is mostly explained in terms of pulsars. Here there are some of the simulations of pulsars young and close by, and they can fit the data. Nevertheless, also dark matter can still fit the data. This is one model of dark matter, very heavy, 1.2 TeV mass, which can fit the data of the positrons. Regarding cosmic ray fluxes, I will just, as I said, you know, the fluxes were expected to be fitted by a single power law, as we will see much better than I can show you in, I'm sure, in Tori's talk. This is not the case anymore because the spectra turned out to be not at all a single power law, but they show an hardening and a softening two very clear regions in the rigidity regime. But this again, I leave this to Tori's talk. I come to the conclusion regarding future experiments. So we are now waiting for the launch of the GAPS balloon. Marco has already mentioned this. This is really ready to launch. It's in Antarctica at the moment, waiting for the good winds to be launched. This is a measurement. This is a balloon experiment of NASA, Italy, but also Japan, which is going to measure anti-deuterons and anti-protons in cosmic rays. Regarding high-energy cosmic rays, we will have most probably in 2027 the third launch on the Chinese space station. This still has the collaboration also with Italy, only on the, let's say, only on the scientific part. This will be a very important mission for cosmic rays. And as has already been mentioned before me, regarding Italy-Japan collaboration, we will have new steps in the JMUSO program with the PBR balloon launch. This will be on the talk of Mario after me. We will have the Lightbird. This was mentioned quite deeply before me. This is not really a cosmic ray measurement, despite we work in the same direction, which is cosmology and dark matter searches. So there will be the Lightbird for the CMB measurement. And let's say in the line of what we have done with the XS missions, there will be the Solar Sea mission where also ASI is involved and INAF are involved for the solar part. So I conclude with saying that this is a very hot field, as it has been said before me. Astroparticle physics is fascinating, rich, and is bringing a lot of results. And from this point of view, I think the Italy and Japan collaboration really will play a leading role, are playing a leading role, and will play it more in the future with the future missions. So I thank you for listening, and I hope I was not too fast with my presentation.
Thank you. Thank you very much, Roberta. No, you were exactly on time.